Welcome to the fourth video in the series. The topic this time is quantum field theories. We are going to use many things from the previous videos now, and we will go through examples of different quantum field theories, QFTs, and we will start with the simplest one, the most easier theory to build, and then we will add certain things to it, and we will add mass, and like we will give interactions and external forces into the theory. So with this, we get to more and more complicated theories in the end. In the end of the video, we will give a recipe on how to make a field theory into a quantum field theory using what we learned in the quantum lecture. So let's get started with our first quantum field theory. Finally, we will discuss our first quantum field, which is going to be the scalar field, the massless scalar field. So 4.1 is the massless scalar field. Maybe a bit of a notion related start that earlier we were discussing the special relativity where the characteristic constant was the speed of light, and now that we were discussing quantum theory, the characteristic constant was the Planck's constant, h bar. So now that we are kind of merging these together, that means that our theory will contain both the c and the h bar, but just for convenience, we will set the value of these to 1. So c will equal to h bar, and that will equal to 1. This is called the natural units. So we will discuss all quantum field theories in the natural units, and there is another change which I'm going to say, that I am going to denote the 4 vectors just with the x. So what used to be x mu, I'm going to call that x. And then if I refer to the spatial part, so from this the spatial part is going to be the x vector, like this. And if I really want to be discussing time, that could be the x0, or maybe I will not with t. Okay, so let's jump into the massless scalar field. So first of all, what does this really mean? We were discussing that fields are essentially mapping between two things, the space-time and the field itself. So the scalar field is going to be denoted with phi, and the phi maps something from the x, which, as you remember, is space-time. So we understand this as a mapping between space-time, which is a 4-dimensional set of numbers in real numbers. So from this we map into, well, we could map into either real numbers, or we could map into the complex numbers as well. So first, let's just do the real numbers, and then maybe in one of the exercises you can deal with the complex numbers. So we were discussing that really to have a theory in physics, what you just need to find is the Lagrangian. So if you know the Lagrangian, then you will know the equations of motion through the Euler-Lagrange equations. So actually what we need is the Lagrangian density of that field. So the Lagrangian density for the massless scalar field is denoted as, or it is the 1/2 times the derivative of the field multiplied with the derivative of the field again. So this means that this is the 1/2 times the derivative of the field, like this, squared. You can kind of establish this just by thinking about it. In a classical case, you have, for the energy, you have 1/2 m v squared, where the v is the derivative of the coordinates. So here again we have the derivative of the coordinates, or not the coordinates but the field itself. We have 1/2, and well, this is the massless scalar field, so it's not a surprise that there is no m involved here. We can extend this Lagrangian into, like going through, so first of all, maybe we can also mention that we have a repeating index, so that means this is an Einstein summation. So we could just think about to defactorize the time component, so I can have the derivative by the 0th component, so that's the time component of the phi, and then take the square of it, and minus the rest of the derivation, 1, 2, 3, which is equivalent to the nabla. So that's going to be nabla phi squared. It just means nabla phi times nabla phi. So we, in the previous lecture, introduced the Euler-Lagrange method to find the equations of motion. So let's just do the same thing. We will use the Euler-Lagrange equations. So in that, we have the derivative of the L, so the derivative of the Lagrangian density by the phi. That is, in this case, will lead to 0, since we only have the derivatives of phi in this Lagrangian. We don't have phi itself. And then when we do the derivative of the Lagrangian by the phi derivative, which does exist in this equation, we get that is the derivative of the phi itself, because we had, this was our Lagrangian, right? So we had the derivative of the Lagrangian on the second power, half of it. When we do the derivative, the 2 comes down and cancels the 1/2, and we just left with the derivative of the phi. So let's put these two together and apply the Euler-Lagrange equations. So in the Euler-Lagrange equations, we have the derivative of the L on the left-hand side, and that equals to the derivative of whatever we had in the right-hand side. So that was now the derivative of the d mu phi. So if we want to again expand this, like we did earlier, this is the same thing as saying that we take the derivative of the phi by time twice, and we subtract the nabla squared of the phi, and that equals to 0. And you could also denote this with the box phi, because this is something which we have seen earlier. So box phi equals 0, and this is something that could be familiar from electromagnetism. So electromagnetism, EM, has the same equation, and from that we know what is the solution. And the solution to this is, well, so in the electromagnetism, this is called a wave equation, and the solution has the form of phi, which depends on x and t. Like this, it's again just the coordinates, a different notion. It is the sum for some p of ap exponential of minus I energy, which corresponds to this p momentum, times the t minus the p momentum x the space part of space-time. So this AD minus ET minus px is something which we see in electromagnetism, and so this is called the wave equation, and this is the wave solution. So this describes waves. So if we insert this back to the original equation into this thing with the red, then we get the so-called dispersion relations. So dispersion relation, dispersion relations. That's an equation between the energy and the momentum. And so after we put it in, we get, because of the derivations, we get the energy down, and we get that this is going to be that the energy corresponding to this momentum p, which is the vector, is the same as the speed of light. Now plugging that back for a second, times the absolute value of the momentum. So this is the theory of particles which have no mass in them. So for example, a photon could be an initial idea that this could be maybe something that describes the photons. Obviously, it's a bit more complicated, but for now, we could think about that as an example. But it's really describing any kind of particle which has no mass. And there is also no interaction in this model yet. So these particles, if they just meet each other, they just propagate through space-time. Their speed is the speed of light, and they do not interact. There is no scattering. There isn't anything. They just go very happily in the universe with the speed of light. Let's now upgrade our scalar field that it has mass now. This is going to be 4.2, the massive scalar field. Massive particles field theory. As I said earlier, we really just want to use the Lagrangian to define the theories. So earlier we had this 1/2 the derivative of the field squared. So now we need to add a term which now includes the mass of the particle. So this is going to be something like a potential energy of the Lagrangian, and so it has to be proportional to the magnitude of the scalar field. So phi, so whatever is here has to include now phi, and we have to have the minimum in the potential energy. That means that whenever we do the derivative, then we need to make the factor down with 1. So it has to be of an even power of the phi. And so that means if you want to take the simplest case again, then this phi will be on the second power because we need to have it an even number, and the lowest even number is 2. And maybe it will lead to nothing, but let's just give it a try with this one. And we will have the factor with m squared, and we also have a 1/2 as a convenience for further convenience, and we have a -1 here too. We really don't know what m is at this point, so this is just a parameter here. Just parameter. But obviously, this is going to be the mass of the particle later on. So we use the same methods. We will take the derivative of the Lagrangian by the phi. This was 0 earlier, but it's not 0 now. It's going to be I take the derivative of phi squared, so that's going to be 2 phi, and that destroys the 1/2, so I am left with minus m squared phi. That's the left hand side of our equation. And then the right hand side, it's very similar to what we saw earlier. We take the derivative of the Lagrangian by the derivative of the field, and the phi derivative squared is just going to be 2 times the phi derivative, and that destroys the 1/2, so we are just left again with a derivative of the phi. And so when we plug this in into the Euler-Lagrange equations again, we get that this is going to be the Klein-Gordon equation. So because we have the derivative of what is in the bottom, so the mu of the mu phi equals to the minus m squared phi. And if I rearrange this, then you know that to be like this, the del squared, and we have plus m squared acting on the phi, leading to 0. So now we have the Klein-Gordon equation. It was really the outcome of this simplest try we had for the Lagrangian, which had an m terminate. And so the solution for this has the form of again the phi, which depends on the space coordinates and the time coordinates, is the sum for p of again the creation operator with the p. Well, for now it's actually not an operator. For now it's really just a factor, a coefficient here, and then we have the exponential of minus I, the energy corresponding to that momentum p multiplied with the time minus the p and the x. This is the solution to this equation. And if we insert this back, then what we find for the equations of motion is that the energy corresponds to that momentum p squared is the same as p squared, and again if I want to plug back the c's, c squared plus m squared c to the power of 4, which was the formula from Einstein. This is the Einstein's energy momentum relation. If we take the special case that the particle is not moving, so p is 0, then we indeed get back that m is really the mass of the particle, and that parameter was describing this thing. But so this was really now the outcome of the theory which we set up, not really an input to the theory. So then let's put some interaction into the picture, right? There is always interaction in nature, otherwise it's going to be boring. So 4.3 is that we have an external force. We can do this, we can add an external force by introducing another potential term or an external potential, also sometimes called as the source current. So let's say this, source current, denoted with J, and it depends on spacetime. So if we include this term in the Lagrangian, we should keep everything that we built up so far. We have the 1/2, we have the derivative of the phi squared minus the 1/2 times the m squared phi squared, and we have this j term with the phi on the first power. Again, we don't know what that means. We will show it later what it could be, and so when we go through again the equations of motions, we do the same Euler-Lagrange formula. Then we get that the equations of motions are the derivative squared plus m squared, as we used to have it in the version with the massive scalar field. But now the right hand side is going to be jx. So this is now an inhomogeneous partial differential equation, and in general, it's not easy to solve this kind of equations. As a next step, let's do a special case. This special case is going to be the so-called phi to the power of 4 or phi 4 theory. So 4.4 is the phi 4 theory. That means that we will replace this j term with a term that has the phi on the fourth power. So Lagrangian is 1/2 the derivative of the phi squared minus the 1/2 m squared phi to the second. This is nothing new. And what we say is that now we have a term which goes with phi to the power of 4. We have some coefficient here, which we will call lambda. And again, there is going to be some random number here, which is 5 to the 4 factorial. We will see why that's a good choice. But anyway, this is really just a convention for later use. So we earlier saw that what happens when we solve the equations of motion, Euler-Lagrange equations lead to the squared plus m squared acting on the phi field leads to the derivative of this term. So that derivative of phi to the power of 4 is going to be phi to the power of 3. You have the 4 coming down, and that was kind of one of the reasons why we used 4 factorial, because now it's going to be 3 factorial, and so we still have the lambda up there. So this lambda is the coupling constant, and it is responsible for showing how strong the force which we included here is. So this could potentially be theory of Higgs boson. The Higgs boson, we know, is a boson, so it's a scalar particle, and we know that it's also massive, and it also could interact with itself, and that could be described by the phi 4 theory. It's really just an interaction between scalar particles, and we will actually in the upcoming lectures we will discuss a bit more in details what can we really do with this, how can we have the Feynman diagrams of this, and what really is the meaning of whatever it seems to be very abstract at this point. But for now, let's just move on. Next example is the scalar field with complex numbers. So this is 4.5 is the complex scalar field. So finally, we map into the complex numbers, not only to the real numbers. So for that, we need to say that we have two scalar fields, phi1 and phi2 are both real scalar fields. And so, like this is just the example of showing that A and B are real. Then from them we can create A plus B times I to be the complex number. So on the same way, we will introduce that we have psi to be a complex field, which is the phi1 plus the I times the phi2, and we will actually add an extra factor of 1 over the square root of 2, which is again something which is we'll see later. We can take the adjoint of this. It just means that we take the complex conjugate, so phi1 is unchanged, but the phi2 factor is now going to be minus I, since that's the part where the complex conjugation has an effect. So this leads to a new Lagrangian with this new variables. So the new Lagrangian that we get out of this is going to be that we take the derivative of the psi plus or psi dagger, and we multiply that with the derivative of the psi. So earlier we just had the derivative of phi squared, but that really meant derivative of phi times the derivative of phi. But now that and then in that case, phi and phi star were the same thing. The complex conjugation of a real number is the same as the original number, while this is not true for complex numbers. So we need to defactor these two things now. And so we have again the mass term and squared, and we had a phi squared here, which now is changing to psi dagger psi. Next step is to introduce the canonical quantization machine. So 4.6 is the canonical quantization machine. So for now, we were discussing all these theories, we lead to fields and so on, but there wasn't really too much quantum mechanics in that. So now this is the way to make things quantum, what we have been discussing so far. We can give a recipe, essentially. So the first step to do is that you write down the Lagrangian. So figure out what is the Lagrangian. That's really the first step. That's what we were doing so far. And actually, this is the most difficult and most complicated of them all. So after that is done, we calculate the momentum density. That was denoted with the uppercase pi mu. So that was the momentum density. And if you know that, then you should also figure out what is the Hamiltonian density, which was the H with the curly version. The next step in our recipe number 3 is that we will treat the fields as operators. So that's really what quantum mechanics is, that we deal with operators. So phi is going to move to phi hat, and the pi is going to move to pi hat, and so on. And then step 4 is that we expand these fields in terms of creation and annihilation operators. So we describe the field as something which goes with the A and the A dagger operators. So let's give some examples for this whole recipe. 4.6.1 is going to be for the massive scalar field. So the first step was that we write down the Lagrangian. This we already have done. So the Lagrangian was the 1/2 the derivative of the phi times the derivative of the phi. So that's the derivative of phi squared minus 1/2 m squared phi squared. Step 2 was to calculate the momentum density. The momentum density was defined to be the derivative of the Lagrangian by the derivative of the field. So in this very specific case, this will lead to saying that if phi mu is the same as the derivative of the the pi mu is the same as the derivative of the phi, right? So we just did the derivation here. This term gives us a 0, and the second power destroyed the 1/2. And then in the same step, we also calculate the Hamiltonian density. Hamiltonian density was defined to be the zeroth component of this pi times the phi minus the Lagrangian. So then again in this case, this leads to the 1/2. So Hamiltonian density is the same as the 1/2 the phi divided by time, which I denoted as phi dot squared minus plus of 1/2 the nabla of the phi squared plus 1/2 m squared phi. I actually didn't include that this is also a derivative. So that's when you take the zeroth component of this, that's going to be the time derivative of the phi multiplied with the time derivative of the phi is the phi derivative squared, and then including that that this was the Lagrangian. When you do the subtraction, then this will lead to the 1/2 factor, and our minus 1/2 and phi is going to become now plus 1/2 m squared phi, just because we were subtracting the Lagrangian. So the next step, number 3, step number 3, was to treat the operators as, or to treat this phi and pi as operators. So pi 0 is going to be the pi 0 with the hat. So we also we learned in the quantum lecture that the relationship between the momentum and where we are, the p and the x, or usually earlier we also use the q, is the same as I h bar. So this was the Heisenberg relation or equation. And so we have the same thing for the field operators. And so these are the equal time commutators for the field operators. So that's actually kind of important that this is the equal time commutators. So that equal time should be denoted as the t. So that this is the t moment when we are looking at these operators. So phi operator now, which is at x space-time and x space and t time, and we take the commutator of that with the pi 0 momentum density at the y, so it's a different location but the same t time, and so that's going to lead to, again, we have an I factor, but then we have but also we could have the h bar, and then we have the so-called Dirac delta of these x and y vectors. So the Dirac delta is a distribution, and it's only non-zero where when this is zero in the body. So when x and y are the same, and this is non-zero, and otherwise it's zero, and also the integral of this is 1. So now that we did this, let's now look at what happens if we take the commutator of this phi at the point x and the time t with another field operator which is located at the y point and the t time. So this is actually going to be exactly the same as if we would do it in the other way around, that we take the dagger of these fields, so phi dagger at x and t commuted with the phi dagger of y and t. So these are actually both just 0. And we can also take the commutators of the momentum densities. So the pi 0 at x and t is the same. This is vector with the pi 0 at y and t is the same as the dagger of it. So taking pi 0 dagger operator with the at the point of x and t commuted with the same thing at y and t is 0 as well. This is kind of equivalent of saying that x with x is 0, p with p is 0, but x with pi is non-zero with p. So the analogy is that this was x and p, this was x and x, and this was p and p, just with the fields. Obviously everything here was an operator. Okay, so coming back to the recipe, our last step is to expand these fields as creation and annihilation operators. So that was number 3. That was number 4. So how will our operator look like? Earlier, we discussed that we can build up our field from creation and annihilation operators. So let's say which we are going to call this field operator as psi, as we did it earlier. So psi dagger is going to be a certain sum for some index p of the creation operator a dagger, and we had this certain sum as the we had minus I b x, and we also had some normalization factor here. And we also had that psi is the same as some other normalization factor, of the sum of the A's, AP's. This is an operator too. And the change is that from the minus I, we move to a plus I, P, X. So these are actually the three vectors. So these are the fields which create particles and the fields which destroy particles. And we are kind of mentioning this in the past, that these quantum fields you should imagine as this continuously changing creation and annihilation of particles. That's also the vacuum. So we could say that then we want to build up our phi scalar field, which is an operator at a given space, is going to be a kind of the sum, a continuous sum of these two things. So we will add the AP dagger operator with the exponential of minus I px, these are three vectors, with the other operator with the AP with the exponential of plus I px, three vectors. And so I said that, and then we had this normalization factor, and I said that we kind of want a continuous sum. So continuous sum means that we take an integral. We take an integral, and we also, for a given space, it's called the integration measure. So this the gamma here is the integration measure. So you know, like in the past, we were using px and dA and dv. So all of these were integration measures. So examples were dx, dA, or dv were all integration measures. We don't really know what this is now, so that's why I'm just denoting it with d gamma. So let's just think about it, what this integration measure could be. So originally, we had the sum for the momentum, the three momentum p. So probably this integration measure will be proportional to the momentum space. So there is going to be a dp3 space in that. So the only thing which we now need to do is to think about how this can become relativistically invariant. So then we lead to the relativity invariant measure. So the original problem is that if you just have dv, when you go faster, the lengths will contract. So that's not something which is invariant in that sense. And so we need to figure out. We have to have certain factors so that it will be relativistically invariant. So the d gamma together actually with the normalization is going to be the d cubed p divided with 2 pi. This is just the number pi, 3 over 2. So we take the 3 over 2 power of 2 pi, which again is just a convenience factor for some later usage. In these all of these numbers are, and kind of could depend on how you introduce them. And you have 1 over 2 times the energy corresponding to that p momentum under the square root, so on the 1/2 power. So this is the integration measure. Okay, so this was a somewhat short video since all the upcoming videos are going to be about what we learned here, and it's going to be an extension of these QFTs, and we will also discuss their application in 2 lectures from now. In the exercises in this chapter, you will find a problem about the generalization of the phi-4 theory, and there will be some examples and problems about the equations of motions from the Lagrangian, especially with the one which is about the complex scalar fields. So that's a very interesting exercise, as the physical outcome of that is that we have now a theory that describes the differences between matter and antimatter. In the next video, we will be discussing the theory of electromagnetism, which is also called the quantum electrodynamics, QED, and then we will actually extend it further to the theory of standard model. So, see you next week.